Math and Beats. We're continuing this pre-calculus discussion, and in this video we're going to discuss linear functions. Think of it as an introduction to the topic, and in a video that will follow this one we'll look at a couple more of like application-based problems. So let's get going. Linear functions. All right, what are they? Well, here's the definition. Definition of a linear function. A linear function is one that can be written in the form right over here. Say this function f of x, which is m times x plus b, and m and b are some real valued constants. So obviously the x is the input here, some number m times the input x plus some other constant b. Any function which has this form is considered to be a linear function. So what do these things mean? M and B, what do they look like graphically? That's what we're going to take a look at in this video. All right, what else? Well, let's just get going and plot a few of these linear functions. And we can do this just by simply plugging in various values of the input x and see what kind of pattern we get. So in the first one, part A here, we have the function f of x is 2x plus 1. So make a little table. If x is 0, then we get that f of 0 is 1. We'll go and plot that 0, 1 right there in blue. How about if x is equal to 1? Then f of 1 is equal to, we'll just plug it in, 2 times 1 plus 1 is 3. So 1, 3 is part of this graph. And let's pick a negative value too. How about when x is -1, then f of -1 is equal to, well, we got 2 times -1, which is -2, plus a 1 is a -1. So at -1 for the input, the output is -1. Now you can already see these three dots are sure looking like, if we connect them, it looks like a line. And sure enough, it is. So let's go ahead and plot that line as so. Get it as accurate as possible here. And there is our first example of a linear functions graph, which is 2x plus 1 equal to f of x. So here's the graph of f of x. Now notice, in this particular example, remember our general form was m times x plus b. So for f of x, we had that m was 2, m times x, 2 times x, and b was 1, plus that b. So there's one line. I'm going to switch colors so we can distinguish between the different lines here. How about we'll pick red for g of x. So for g of x, off on the side over here, I'm going to do this on the right side. G of x is -1/2 x plus 1. So if x is 0, we get that g of 0 is equal to 1. So 0, 1 is also on the graph of g of x. How about if x is equal to 2? What do we get? Well, g of 2, plug it in, that's a -1/2 times a 2 plus a 1, which is equal to -1 plus 1, which is equal to 0. So when x is 2, this function g is 0, 2, 0. And then maybe one more. How about when x is equal to, say, -2? Then g of -2 is equal to -1/2 times -2, and then plus a 1, which is equal to 1 plus a 1, right? -1/2 times -2 is a 1 plus a 1, which is 2. So when x is -2, we are at the output of 2. And here we can see that this graph connecting the dots also is a line. So let's go ahead and draw that line in as well. Move my other side around here a little bit, make it a little more accurate. There we go. There's the graph of g of x. Now notice, again, the general form mx plus b for g, m was equal to -1/2 and b was equal to 1. The meaning behind this m value and b value we're going to discuss, but right now just kind of verifying what they are, identifying them and whatnot. All right, so we got two different lines so far. And for the last one, h of x, well, h of x is equal to 3. So in that form, m times x plus b, notice that this is the same as 0 times x plus a 3. So really, in this case, m is equal to 0 and b is equal to 3, just keeping it in mind. Now for this function, we call it a constant function because no matter which value of x we plug in, it doesn't change. It's always 3. So if x is 0, we're at the output of 3. If x is 2, we're at the output of 3. If x is -2, we're at the output of 3. So the function is just always equal to 3. And because of that, we call it a constant function. So go ahead and draw the graph of that one here. And there you go. That's the graph of h of x. Notice that that line is a horizontal line, right? And that has to do with the fact that the value of m is equal to 0. So we just get going here, drawing some graphs by simply plugging in some input values for x. And we see that, we say it's a linear function, and their graphs are lines. Go figure. So we can be more efficient with this. We don't always have to plot the points. Let's dive into more about what the values of b and m really tell us when we look at the graph. So as we just saw, these graphs are lines. And here's just a generic picture of a linear function, calling it y here equal to mx plus b. Think of it as some function f of x if you want. And notice that anytime I plug in x is 0 into this function, I will be left with b. So right here, you see that point on the graph, 0, b. Really, this value of b is telling us where we are located on the y-axis for this particular function. So the b value, 0, b, as an ordered pair, is always, as we say, our y-intercept. Where does the function intersect the y-axis, the vertical axis? So the value of b is always that vertical position on the y-axis. So that's instant. We could get that instantly once we have the formula. Now for the value of m, we have to go off to the side here where you see this triangle going on. And what I've shown in the graph is two different arbitrary points on the graph of the line. Let's call them right here x1, y1, and then this other point over here, x2, y2. So it's just two different points. It could be any points, right? It could be really far away, they could be really close together. And so if I go and I look at how far I've gone from the different horizontal positions x1 and x2, well, that distance between the two different x values is x2 minus x1. I just subtract the smaller one from the larger value. Correspondingly, the amount of change I've gone up or down on the graph of this line over this particular interval of x's is the outputs y2 minus y1. That change over here, the vertical change. And it's supposed to be telling us something, right? So if I move left or right by some amount, say x2 minus x1, I've gone up or down this amount y2 minus y1. Now, if I make a smaller triangle here, notice that that triangle is a similar triangle to the bigger one. And we'd like to know, well, if I go some different distance in the horizontal direction, how much have I gone up or down? And the claim is that it's the same amount no matter how far you move left or right. You're always going to go up or down by that same amount. It's just proportional. So you go back to these graphs that we looked at before. Notice for the blue graph, f of x, the m value up here on the top left was 2. Okay, so if you look at the graph of f and you look at this idea of m, notice that if I start at 0, 1, remember this b value 1 is telling us where we're located on the y-axis. In this case, it's 1. If I go from there, x is 0, and I move over 1 unit to the right, well, how much have I gone up or down? In this case, I've gone up or down by 2 units, right? And in fact, the ratio 2 over 1 is equal to 2. So in this case, for f, m was 2, and notice it's the same as 2 over 1. Go to a different point on the graph. Say at x was -1, we were at the output of -1. If I move over 1 unit, right, I go up again by 2 units. Again, we get that value as a ratio. The output change over the input change is this value m. In fact, if we go to the red graph of g, and remember that for g, the m value is -1/2. In this case, let's just go to the ordered pair -2, 2. Notice that if I go down 1 unit from there and move to the right 2 units, well, here I've gone down by 1 and I've moved to the right by 2. So the difference between f and g here is that f is an increasing function, right? It's getting larger as I move from left to right, whereas g is a decreasing function. It's getting smaller in output values as I move from left to right horizontally. For this reason, this slope, as we're going to call it, m, is -1/2 because I've gone down. The output change is negative now since the outputs here as I move from left to right over this interval from x is -2 to x is 0, right? I've moved a distance of 2 units to the right. Now I take that change in the output direction, where the change in the output direction is actually a 1 minus a 2, which is a -1. So in this case, the m, right, I've gone down 1, hence the negative, and I've gone to the right 2. Again, this change in the output direction over the change in the input direction. So this is this idea of m. M is called our slope. Let's go back down to the generic graph. The m here is called our slope of our function, and it is simply the ratio of the change in output values over the change of the input values. So in this case, how far have I moved up and down? Well, I've made a change of y2 minus y1 over that arbitrary interval that we had, and I've moved in the horizontal direction x2 minus x1. So this is what we call our slope, and for lines, it's constant. That's a big thing. For lines, or as we're calling them, linear functions, m, which is your slope, is constant. That is not true in general for other curves, right? As we're going to dive into in a video that's a couple ones from now when we look at rates of change and whatnot. Lines, though, have constant slope, as we say, and that slope is this ratio, change in the output over the change in the input over the corresponding interval, keeping in mind we should be consistent with the order in which we compute these slopes. So it's a really important underlying concept behind a linear function is this idea that they are linear, their graphs are lines, and as I move from left to right, how far have I gone up or down? The same amount, no matter what interval I pick. Constant slope. So it's pretty nice idea here. Now this leads us to a different couple of forms of lines that we like to refer to. One is called the slope-intercept form of a line. That's this form right here, mx plus b. So that's the same form that we've been looking at. And when you write it as a function notation, say f of x, that's our standard notation. We call it slope-intercept because when we write it that way, the m is sitting right in front of us, right? That's our slope. And our b value, which is the vertical location of the y-intercept, is sitting right there as well. So the slope-intercept form, hence because it's just sitting there in the actual notation for the function. So 0b, remember, y-intercept. So there's that form. That's the form we would use if we're going to use function notation. Another form that sometimes we use is point slope form. So this is in the situation in which we have some point that we know of on the line. Let's say we know this point x1 comma y1 and the slope m, right? If we know what that slope is, then the equation of the line can be found by writing this statement right here. That's your point slope form. Y minus the input, or the output, excuse me, y1 is equal to the slope m times x minus x1. Notice if I solve that for the output y and I add y1 to the right hand side, then I could write it in the slope-intercept form right over here. F of x is y1 plus the slope m times x minus x1, which can be rewritten, of course, in mx plus b form. If you were to write that out, you'd have an mx by distributing the m, and then plus that y1, and then minus m times x1. Remember, keeping in mind, we know what m is, the slope, and we know what x1 and y1 are from that point that we're given. So point slope is, used really if we know a point and we know the slope, then we can find the slope-intercept form and hence the function notation for the linear function by using the point slope form right over here. Look at just a couple of examples of this to see how we could use those two different forms to find some equations of some linear functions here. So in this example, we want to find the equation of a linear function which has the point 1 comma 4 and which has slope negative 3/4. So this is a situation that we want to use point slope form because we have a point and we have the slope. So we know that the slope m here is negative 3/4, and then we have this point, remember in our form above, that's like your x1 comma y1, right? So then the point slope form says, okay, well, if we want to find the equation of the line, then point slope form is going to be y minus, all right, that output value of the point we have, which is a 4, y1, equal to m, the slope, which is negative 3/4, times x minus the input value at the point which is a 1. So there's your point slope form. But that's not the equation of the linear function, right? We want to isolate the output variable y, so we can write it as y is f of x. So I'm going to add that 4 to both sides. And I'm going to get y is 4, right? Add that 4 to both sides. And then I'll go ahead and distribute the negative 3/4 to the x minus 1. So I'm going to have a minus a 3/4 x, and then plus a 3/4, right? Negative 3/4 times that negative 1. Now, collecting like terms, we see that we have a 4 plus a 3/4. So, of course, 4 is a common denominator. With 4 is the same thing as 16 over 4, right? Minus the 3/4 x plus the 3/4. And then finally, if we just add those together, we get that y, which is the function, say it's called f of x, is equal to negative 3/4 x plus a 19/4. And now it's in that slope-intercept form, the equation of the function. The slope is negative 3/4. We already knew that. But then now we know the y-intercept is 0, 19/4. So there's one example. Oftentimes you have to find equations of lines when doing other things in mathematics. Let's look at one last example here in which what we're given is just 2 points on the line. So in this case, we want to find the equation of this linear function, which has these 2 points, 3, negative 5, and 2, negative 7. Now, what do we do here is the question. We have to think back about what we need to find the equation of the line. We either need the slope and the y-intercept, neither of which we have here, or we need a point and the slope. So we definitely have a point here. We actually have 2 points, but we don't have the slope. But remember that we can find the slope, right up here on the top left. If we have 2 arbitrary points on the line, we can take the change in the outputs and divide it by the change in the inputs to get that corresponding slope. And then we'll use the other point on the line, choose whatever one we want, to use the point slope form and find the equation of the function. So that's what we're going to do. We're going to use the fact that we need to find the slope, m, change in the output divided by the change in the input. Think of the first order pair 3, negative 5 as x1, y1, and the second ordered pair as x2, y2. It doesn't really matter which ordered pair you call which, as long as you're keeping them consistent. So I got to find the change in the output, y2 minus y1, over the change in the input, x2 minus x1. And now we just plug them in. y2 is a 7 minus negative 5 divided by the change x2 minus x1. x2 is a negative 2, and then minus x1, which is a 3. In the numerator, we get a 7 plus a 5, which is a 12, positive. And in the denominator, we have a negative 5. So the same as negative 12 over 5. There's our slope. Now we know the slope, and then we can use point slope form, picking whichever ordered pair we'd like to use as the point of interest. Let's just use x1 and y1 to do that, just like the last one, but you could use the other one as well if you wanted. So then point slope form, what is it? Well, y minus y1, which is y minus a minus 5, is equal to the slope, negative 12/5, which we found now, times x minus x1, which here is a 3. So notice on the left side, that's a y plus a 5, right? So I want to subtract a 5 on both sides to rewrite this as y equal to a minus 5 minus a 12/5 times the x, distributing the negative 12/5 across x minus 3. And then negative 12/5 times a negative 3 is a positive 36/5. Yeah? And then we'll collect the constants together. Negative 5 is the same as negative 25 over 5, common denominator here, minus the 12 over 5 times x, and then plus the 36 over 5. And we get, in the end, this function, let's just call it f of x again, why not, is going to be equal to negative 12/5 x, and then negative 25 plus 36 is a positive 11/5. And there you have it. Now we have the equation of this linear function. Notice that the b value here is 11/5, the vertical location for which this graph of the line crosses the y-axis. So there's a little introduction to lines. We need lines for things that we're going to do moving forward in this pre-calculus 1 discussion. And so what we'll do next in the next video is maybe look at a couple more of these in which we just identify the slope, identify the y-intercept, and then plot them maybe that way, and also look at an application or two in which we really want to interpret the slope in real-world settings, because it's important when we talk about rates of change. So that's the end of this video. Stay tuned for more pre-calc 1 videos, and we'll just keep moving forward with the content. All right then. Math and Beast. See you later.